In this video, we're going to have a look at common denominators, which is really important for adding fractions. And we'll see that the least common denominator is actually a representation of the least common multiple. And I'll show you how to find the right least common denominator in every situation. Today on High Peak Education. What's going on, everybody? I hope you're having just a great day, and I really am grateful that you watch these videos. So in this video, we're taking a look at adding fractions. But in order to do that, you have to imagine that if you're putting, say, wedges of a pizza pie together, the wedges must be the same size compared to each other. And what that means is the denominators need to be the same so that we can add the fractions. But if we're going to have a common denominator, we need a formula, we need an algorithm, that is, we need a process and a procedure to find the least common denominator. So that's what we're going to be talking about today, and it's based on the idea of least common multiple. Now, we've discussed with factorization trees before how the least common multiple is related a little bit to greatest common factor in these factorization trees, but we're going to today find out how to find the least common denominator. So let us get into today's content. I'm going to have 2/3 now. Okay, so that's 2/3, right? I've got a circle, and that's 2 wedges out of 3. But what are we doing? We're adding this to 5/3. Now 5/3 would be, that's like 1 whole and how many other thirds?
2 other thirds.
Right. You see that there now. So the $1 million question is, what does this create? Well, it should create 7/3. So do you see that we could take this wedge and put it in there, and then we still have 1 more wedge. So you should have 7/3 left. 7/3. See how that works? So the idea is that, like, part of the reason you know that you don't add denominators is because think of denominator as like the cuts or the number of wedges there. Do you see that there's 3 wedge spots here? Now the 3 wedge spots is reflective of that 3 right there. It's thirds. And then again, there's more 3 wedge spots here, right? But we've got 5 of them. So we've got, 1, 2 here, but here we have 1, 2, 3, 4, 5. You see that?
Yeah.
We go 1, 2 plus 1, 2, 3, 4, 5. We get 7, right? There's 7 of them here, right?
Yeah.
7 3 wedge spots.
Okay.
And you can just see that visually. So, I mean, let's put it this way. Anytime we make an error, the best thing to do is to learn from it. So that's one of my tutoring philosophies, is that don't try to look at getting a math problem wrong as a failure. As long as you fail forward, as long as you learn and don't make that mistake again and realize why it is a certain way, then you won't make that error again. You won't forget it, okay? If you make errors, it's good to make errors early, often, and with understanding.
Okay.
So those are fractions. They already have a what?
A common denominator?
Yes. So these already have a common, okay? So since they already have a common denominator, we just add numerators, right? And then, we can see it here visually.
Yeah.
Okay? All right. Now, with that in mind, let's go one more step and say, okay, how is it that we can add fractions together that don't have a common denominator? Okay? I want to know what happens when you take 2/3 and add 1/6. What are your thoughts about how we might do this?
Obviously, we would find find a common denominator.
Right, so we need to find a common denominator. So first of all, we must find a common denominator. Now, by the way, there are several methods of finding a common denominator. It turns out you can actually find something that's like a less optimal, like in other words, the numbers are bigger. When I say less optimal, what I also mean is you can find a denominator that'll work. In fact, what some teachers will tell you to do is some teachers will tell you, oh, just always multiply them together, 3 times 6. Now that finds a common denominator. That will find a common denominator. That'll work, but in this case, I wouldn't recommend it. In fact, I'll show you that method afterwards, and you'll see why it's less good. But for now, let's try to do it the right way. What did we say a few minutes ago is the kind of denominator that we want to seek? Right, we seek the least common denominator. That's the LCD, often abbreviated, okay? The least common denominator we seek. Now remember, least common denominator is predicated upon least common what?
Multiple?
Yes, the least common multiple, okay? Now, how is a multiple different than a factor? Well, we have to ask this question. I'm going to suggest we go back to the factor trees. Now, 3 is what sort of a number? We've talked about these kind of numbers before.
Prime number?
Yeah, you can't do a tree for it, can you? Any prime number, there's no tree, just 3 and 1. But how about 6? 6 is still composite. There's only 2 factors aside from itself and 1. 2 and 3, okay? So here's the deal. Listen to me for contrast here. The greatest common factor, this is a review of a few sessions ago. The greatest common factor of 3 and 6 would be what? It's going to be 3 itself. Remember what the word we said with greatest common factor was? The greatest what? Shared. Shared is the key word. That's why each time we've done this, I've circled the number because we're circling prime numbers that are shared.
Okay.
Okay? By the way, also, the greatest common factor will always be less than or equal to the number. Generally, this thing is smaller. The greatest common factor of 3 and 6 equaled 3, but 3, given it was the greatest common factor, was less than 6. So generally it's equal, but usually smaller, right? Now the reason I bring that up is because the greatest common factor is completely different than the least common multiple, or at least it's not too different, but it is different. Let me give you sort of the words as opposed to greatest common factor. With least common multiple, at least one of take exactly one of each of the prime factors. Take exactly one of each of the prime factors. What that means is, for this relatively simple example, the least common multiple of 3 and 6 is going to be 6. And let's think about why that is. There's 2 ways you can think about this. Number 1, with least common multiple, we need to take both of these because they're both different. But the thing is, this is repeated, the 3. So we don't need to take it again. We've already got it. Okay?
All right.
The other way to think about this, and this is sometimes a more useful way, start listing out the multiples of 3. So what would the multiples of 3 be? So it'd be 3, 6, 9, what's next? And so on, right?
Yeah.
Okay, so you can just keep going. What are the multiples of 6? So we'd start off with
12,
18, 24, and so on, right? Now watch this. This is an important insight. What's the first number in their lists that they share together? Do you see that? That's a key insight.
Okay.
Let the word sink in. Least common multiple. It's the smallest number, least common, that they both multiply up to, right? In other words, it's the smallest number in both of their multiple lists.
All right.
Does that make sense?
Yeah.
Okay, now the reason you're going to have that is because, well, look at this. This is just 3 times 2. That's what we see right there. But then 6 is just 6 times 1.
Okay.
So what I'm trying to say is this. The least common multiple is the same thing as the least common denominator as long as we apply least common multiple to the denominators. So basically LCM and LCD, part of the reason the abbreviations are so similar is because they're basically the exact same thing, except you use least common multiple, but the numbers that you use are denominators that you have.
Okay.
That's all I'm saying.
All right.
Now, with that said, here's what we want to do. We want to take 2 out of 3, 2/3, and we want to multiply it by something. We want to multiply it by something to get to be the same denominator as 6, right?
Yeah.
Because, by the way, since 6 is the least common denominator, we don't have to change the 1/6, right?
Okay. All right.
So think about this. And by the way, you should look at the factor tree, right? What number do we need to multiply 3 by to get 6?
2.
We need to multiply by 2. Because here's the deal. Isn't that the part of the least common multiple that's missing?
Yeah.
Like if the group of numbers is 2 and 3, 3 is missing 2. But 6 is not, because 6 already has 2 and 3.
All right.
So we need to multiply by 2 over 2. Now let's talk about that. 3 times 2 is really our goal, right? Because we need to get a 6 there in the denominator. But why would I multiply by 2 in the numerator as well?
Explain it. It's like.
Okay, so let's try. First of all, if you multiply by 2 at the bottom, 2 at the top, most teachers would explain it this way. In math, you need to be, what's the F word? 4 letters. Fair.
Okay.
Isn't math all about fairness, really? It's like if you have an equation, what you do to one side, you got to do to the other, right?
Okay, yeah.
Right? Like what you do to a denominator, you have to do to the numerator. That kind of seems to make sense, right? So first of all, this is fair. I mean, that's one way you can justify it. It's fair. But in my opinion, that's not like a very good argument. Like why we got to be fair, right? By the way, does that mean if you make more money, you should pay the same percentage of taxes? Well, not everybody thinks so. Sometimes if you make more money, some people think you should pay more taxes, right? Because you have more to spare. So not everything in life is quote unquote fair, right? So let me ask this question. What's maybe a better argument? Think about the number 2 over 2 over 2 is what special number? 1, isn't it 1?
Yeah.
If I diagram this out as a circle, wouldn't the circle look like this? We have both the wedges. 2 halves, right? If you had a pizza that wasn't cut yet and you cut it in half and you have both slices, do you have the one whole pizza?
Yeah.
Sure you do, right? So 2 halves is the same thing as 1 whole. Now let me ask you this. This is so important you understand this. In fact, I just want to briefly a little bit touch on your algebra understanding here to get this idea. Suppose I have any number at all in the world, and I times it by 1. What do I get? Then whatever number you had, right? Anything times 1 is the anything. So by the way, n right there could be anything you want. 5 times 1 is 5. 1,000,000 times 1 is 1,000,000. 11/16 times 1 is 11/16, right? Anything you want. But anyway, the reason I bring all that up is because here's the deal. When you multiply by 2 over 2, you're basically multiplying by 1. And when you multiply by 1, have you changed the value? No. So the thing is, whenever you multiply a number by 1, you can change the form of that number, but you don't change the value of that number. This is an important idea. It's a very important idea. Whatever you multiply by 1, or any form of 1, because could we have multiplied by 4 over 4? Sure, there's nothing wrong with that, right? Because 4 over 4 is 1.
Yeah.
Yeah, that's another form of 1, right? So 1 is the same thing as 4 over 4. In fact, by the way, here's just a brief little preview. If 1 is the same thing as 4 over 4, another form of 1 we'll do in algebra is x over x. See what I'm saying? Because if it's the same thing over itself, that's another form of 1. Okay, so that's an important idea. We're going to keep using that as we go forward, because that always allows us to change the form of a fraction, but not the value. Multiplying by 1 in the same thing over itself. Now, hold that idea in your mind, and then it hopefully should make sense how we get this. What's 2 over 3 times 2 over 2? Well, now we're doing like we did in previous sessions. We multiply both the numerator and the denominator by 2, right? So what do we get? What's 2 times 2? Yes, and what do we get for the denominator? 6. So we get 4/6. Then we have plus 1/6. So what's the result?
4/6 plus 1/6 is 5/6.
5 over 6. So that'd be your answer. What I wanted to do on the next slide is to prove to you why common denominators are so important and how they look visually. Imagine you have the 3 circles downstairs. What do you identify the first circle as?
Oh, that's 2/3.
2/3. Okay. 2/3, we want to add that to what? Like we were just doing.
To 1/6.
Yes, we want to add that to 1/6. Okay, so this is now 1/6, right? Good with that so far. Now, this is key. Do you see that in order to get over here to our final obtained goal? Do you see that the sizes of the slices are not the same?
Yeah.
I mean, if you had a pizza, you could imagine putting this in there, but unless you really understand like fractions, it'd be hard to describe to somebody, okay, how much pizza is left over, right?
Yeah.
If you have 2/3 of one, by the way, let's just say it was like a big pizza party, they were all cheese pizzas, and you have like a 2/3 of a cheese pizza left and then a 1/6 of a cheese pizza left. But then mom says, okay, how much pizza do you have left? Like you've put it in one box, right?
Yeah.
Be nice to know. So if that's the case, then we say, okay, if we put that slice there, here's what we really need to do. We need to take the 2/3 and we need to make it into how many sixths? What did we just say a moment ago? 4/6, because you're multiplying the numerator by 2 and the denominator by 2. But I hope that you see that this is exactly the same amount of pizza that you had before, but just more cuts. Let that sink in for a second. When you're doing a common denominator, you're just doing more cuts. And you want the cuts to be like the same size. You see what I'm getting at?
Yeah.
So now I think we are set up for success. Because look at this. We can now add. Do you see that? Do you see it? We can now add 4/6, which is what we took time to come up with. That's 4 over 6, right?
Yeah.
Now we can finally add that to 1 over 6. And then what do we get? 5 over 6. Does that make sense to you?
Yeah, I think so.
So all we're doing, I mean, think about this. All we're doing is we're introducing more cuts. Let's make another cut here. Let's make another cut here. Let's make another cut here. Do you see that?
Yeah.
And then that creates this circle, right? Now, by the way, also, you assume when you make a cut, think about it's like pizza, assume that no cheese goes on the blade or whatever, right? Like you don't lose any. So
Yeah.
let's assume that like just by making a cut, you don't like lose mass of pizza.
Yeah.
Okay, so, but that's, as long as you have a very sharp knife, that's actually a pretty good assumption. You're not going to get much pizza on the knife at all.
All right.
Okay, but you get the idea, right? That basically all we're doing is we're taking cuts and we're saying, look, let's have 2 over 3, and instead let's rebrand it. Let's multiply by 2 over 2, which again is another form of 1, right? Just another form of 1. And have we changed the value of the pizza, the first pizza? We have not. Certainly the second pizza hasn't changed because it's just the same thing. And then we can finally add them together and get the 5 over 6.
Yeah.
Do you see how that works?
Yeah, that makes sense.
So I know, again, remember I was mentioning before, like, I don't just want to tell you things, like I also want to show you and make sure you're as involved as possible. That you understand what you're doing when you're adding 2 fractions together that are, of different denominators, right?
Yeah.
Essentially, all we're doing is we're just making more cuts, and we're making sure the denominator is the same so that we can add them, which is just like saying the wedge sizes are the same so we can add them. Does that make sense?
It makes sense to me.
3 over 4, and we want to add that to 1/3. So I'm going to take 3 over 4 and add it to 1 over 3.
Okay.
Now this is where we're going to be a little more clever. Remember I said I wanted to do that same last problem for you, but the harder way? I almost forgot.
Mm-hmm.
So let me show you what I mean by that method. And again, let me also show you why I do not recommend that method. It's because the numbers get bigger. So if you did it that way, you're going to have 2 over 3 times, and again, 3 gets times by 6. So you have to do times 6 over 6. And then with the 1 over 6, again, you need to get to 18, so you have to times by 3. Now if you work all that out, you're going to get, let's see, 2 times 6 is 12, 3 times 6 is 18, and then you're going to have 1 times 3 is 3, and then 6 times 3 is 18. By the way, so what you're going to get is 12 plus 3. 12 plus 3.
15.
So you're going to have 15 over 18. But notice we're still not done. You have to simplify it. So what's the greatest, we talked about this before, what's the greatest common factor here? I think it's going to be 3, yes. Okay? Remember, you can do the trees, right? 15 breaks down into what? 5 and 3. Yep. 18 breaks down into what? 6 and 3 is a good start. And then what does 6 break down into? 2 and 3. Remember, we want the greatest amount that's shared. Shared. So we want this and this, right?
Yeah.
Not both the 3's from the 18, just the 1. Because 15 only has 1 3, right?
Yeah.
So if we do that, we're going to end up with 5 over 6, which is the correct answer, right?
Yeah.
We know that that's 5 over 6 is the answer.
Mhm.
But here's the deal. Number 1, do you see how we had to change both fractions? That takes a little longer.
Mhm.
Number 2, do you see that the numbers are bigger? That makes it harder.
Okay.
Number 3, do you see that you have to simplify the final fraction? Okay, so in the case that we had, we didn't have to simplify the final fraction.
Mhm.
You see what I'm saying? So
Yeah.
let's put it this way. You can always get a common denominator. A common denominator by multiplying both numbers together. But that's not necessarily the least common denominator.
Okay.
In fact, in many cases, it is not. Now, for the case we are going to work on here, guess what? If you multiply both denominators together, it will be the least common denominator. But you didn't necessarily know that until you start getting better at this stuff. Does that make sense before we move on?
Yeah, it does.
Okay. By the way, as a quick reason, here's actually a 4th reason why I didn't want to do it this way. Could you imagine what a pizza would look like if you had 18 slices? I mean, it's going to be ridiculous, right? I mean, it's going to be like this, like this, like this, and that's only 8 slices. I mean, we're going to have to go like an unbelievable number of slices, right? Like, and
Yeah.
I don't know what you think, like, that's just way too hard for my brain to handle. Like,
Yeah.
you know, I mean, I can't count up slices that quickly.
Yeah.
So part of it is it's easier to show visually if you keep the numbers smaller.
Okay.
So there's 4 reasons to use least common denominator over just, by the way, sometimes people call this the butterfly method. That just,
Okay.
like take 6 times 2 and you get 12. Take 6 times 3, you get 18. Take 3 times 1, you get 3. Take 3 times 6, 18. You can add them together, okay? So I would not recommend this butterfly method. I would not recommend it. Okay?
Yeah.
It's harder. Okay? Plus, by the way, when we get to algebra, least common denominator is going to be better if we work with least common denominator, especially because we're going to have many things in terms of x and so on. Okay? So, anyway. All right. So let's move on. Let's try another example. So let's try 3/4 and 1/3. So first of all, we want the least common denominator between 3 and 4, right?
Yeah.
3 and 4, which is the same thing as saying we want the least common multiple of the denominators. Denominators in this case are just 3 and 4. By the way, let me just briefly make a comment. See how so far we're adding 2 fractions together?
Yeah.
Is it possible you could add 3 fractions together?
It's possible.
Well, sure. You could add 4 fractions together or 5 fractions together. And guess what? If you needed to do that, you'd need the least common multiple of all 4 or all 5 denominators, right? So it can be done. It's just a little longer. For now, we're building up to higher and higher things. Okay, so just wanted to mention that. But for now, let's think about the least common multiple of, which is like the least common denominator, since 3 and 4 are the denominators. Okay, so once again, 3 is what sort of a number? You said this a few minutes ago.
A prime number.
Yeah, this is a prime, right? You can't divide it by anything but itself in 1.
Yeah.
How about 4? Let's ask this question. Do they share any factors? Yeah, so we're going to say no. So in order to get the least common multiple, what we're going to do is we're just going to take what? Take all the factors. In other words, just take everything.
Okay.
So we need the 3, we need this 2, and we need this 2.
Okay.
So do you see the least common multiple is going to be 3 times 2 times 2, which is 3 times 4, which is 12. Now, just to confirm that, let's do the list, shall we? 3, 6, 9. What comes next? 12, 15, 18, and so on, right?
Yeah.
All right, so then start giving me the multiplication table for 4, please.
16.
And we can stop, because we found what shared one, right?
Yeah.
What's the shared one?
The 12.
See that? So it works itself out, right?
Yeah.
So it's the least common multiple. All right then. So we want to have 3 over 4. And we want to times by whatever it's missing. Now think about this. 4 is 2 times 2. So what is 4 missing? 3. So you're saying if I times 4 by 3, I get 12.
Yeah.
That'll work. If we multiply the denominator by 3, what must we multiply the numerator by? Yes, because remember, that's another form of 1, right?
Yeah.
3 over 3 is the same thing as our friend, the number 1. You good with that so far? Plus, then we're going to have the next fraction, 1 over 3. But 3 is missing what? So here's our friend 3. It's missing what? Both 2's. So what is 2 times 2, by the way?
4.
4, so I can put the 4 down here, right?
Yeah.
And you're telling me that 3 times 4 is 12? What do we have to multiply the numerator by?
4.
Yeah, because we have to retain equality, right? We have to multiply by another form of 1. Okay, so let's work this out. You tell me, what do we get for the first fraction numerator? I agree, 9. What do we get for the first fraction denominator?
12.
That's right, so we get 9 over 12 plus, and then what do we get for the second fraction? What's that?
4 over 12.
So we get 4 over 12. Good job. Okay, so we have 9 over 12 plus, so what do we get when we add those together?
13 over 12.
13 over 12, which, by the way, that'd be the same thing as 1 and 1/12. Now remember, 1 and 1/12, you often just write it as this. That's a mixed number, right?
Yeah.
Hopefully you've seen that before in your life. You can do this visually. So let's try 3/4. Now there it is.
Oh, there we go. Yeah.
Okay, so there's 3/4. Now, first of all, do you see that that's
Yeah.
it's like, okay, I don't see what the size of those wedges are. So we have to get 12ths. So what I'm going to recommend is, think about this. If you're going to add these together, you can introduce your own cuts right here on the bit paper. By the way, that's why we have the bit paper, so we can just draw right on this. Okay? So what that means is we can make this into 12ths. Now let's think about how we make 4ths into 12ths. We multiplied it by 3. So since we multiplied it by 3, I think there needs to be every one of these quarter wedges needs to be 3 wedges. So what do I mean by that? I mean that you've got this, and then you've also got this for that wedge. See that? I was just focusing on this wedge, by the way. Then I need to do the same thing with the other wedges. Now this is not going to be perfect, but hopefully you get the idea. Now look at this. Count them up. 1, 2, 3, 4, 5, 6, 7, 9 12ths, right? That's exactly what we expected, right?
Yeah.
Okay, so it's not just out of left field. It's a real thing. We're making cuts.
Okay.
So then, guess what? We got to make each of these 3 wedges cut by 4. Now this is going to be a little more tedious, right? Because we got to end up with 4 12ths. Oh shoot! I'm sorry. Actually, I did 1/3, not 2/3. Okay, hang on. Excuse me. So now we want to make cuts on the next one, right? Each of these green wedges needs to be cut 4 times. So let me see if I can do this correctly. I think I have to cut it there, and I think I have to cut each of these in half. See how I'm doing that? So 1, 2, 3, 4. 4 12ths, right?
Mm-hmm.
Because we had to cut it into 4 wedges, that's why you multiplied it by 4.
Yeah.
It makes sense?
Yeah.
So anyway, this ends up being 13 over 12. Now, what does that actually look like? Well, it turns out that it's a little hard to show. Hopefully you see that you have these 3 wedges. This one, and this one can go right in here. So that's one hole. Plus, then we have another wedge, right? Let's do orange. So this one, we also have this other wedge, right? This is 1/12. So that's that's a 1 right here. 1 and 1/12, which is 13 12ths.
All right.
And that's how we know it's correct. See how that works?
Okay. Yeah.
Okay, so that's how we add fractions together. By the way, whenever the denominators have no factors, if you use the butterfly method, it would work perfect.
Okay.
Because that's essentially what we did.
Okay.
Now,
Okay.
all that being said, I suggest next time we do some subtraction of fractions as well. And then we also do some other examples where least common denominator is a little bit bigger number to work with. Okay?
Okay.
So we'll do that, and then pretty soon, you'll actually be, believe it or not, kind of like almost like a master of fractions. Because if you understand what we've done the past few sessions, and maybe the next session, you'll be totally good to go.
So what you saw in today's video is that a common denominator is absolutely essential, it's absolutely needed in order to add fractions together. Remember, the least common denominator is the exact same thing as the least common multiple of all denominators. Now for addition problems we did today, we only had 2 fractions, thus 2 denominators. If you have multiple fractions, multiple denominators, you need to take all of the factors from all of the denominators. What that really means is we need all the uniqueness from each of the denominators. So if you think about that, the factor trees are really important because we can break each number down into its prime factors, and we need one of each of those prime factors, and thus we will have the least common denominator. Remember, if the numbers, let's say they're two numbers and they don't share any factors, then you can just multiply the numbers together, you have the least common denominator. That's a relatively easy way. But remember, not all problems, in fact, most problems don't work like that. And that's how some teachers explain it, and I don't agree with that, and I think it ends up being longer and harder. But now you know how to find the least common denominator, and you've seen also visually why the pieces should fit together and they're of the same size when you make more cuts, so that we require having a common denominator in order to add fractions together. So hopefully that all makes sense to you, and now you can use this to add fractions together anytime you need to the rest of your life. Let us know in the comments how you're going to use this information, how it is you're going to help maybe a student or add things together that are in portions and fractions in your life, work, education, research, or otherwise. We appreciate hearing from you very much. We're very grateful for your support of this channel. Thank you so much for watching High Peak Education. Please smash the like button if you enjoy the content to help the algorithm push these videos to higher standing. Please support us on Patreon. Social media links you can find in the description below, also on the description of this channel. There are more videos to come along like this, so stay tuned for other videos in the series where we'll be adding more fractions together and also subtracting fractions, things like that. Thank you for watching, and I will see you in the next video.